In this particular section, we are going to deal with trigonometric ratios of some standard angles. So let me first explain which angles are called standard angles. 0 degrees, 30 degrees, so 0 degrees, 30 degrees, 45 degrees, 60 degrees and 90 degrees are considered to be standard angles. So let us see why it is so easy to calculate the trigonometric ratios of the following angles. We will first calculate the trigonometric ratios of angle 45 degrees. So for calculating the trigonometric ratios of 45 degrees, let us consider that we have an isosceles right angle triangle. So this is triangle ABC, which is right angled at B. And let's consider that the side AB is equal to BC. Now because this is an isosceles right angle triangle, I know that these base angles are going to be equal. So let us calculate the measures of these equal angles. Let this particular angle be x. So if this angle is x, then this angle is also x. So I know that 90 plus x is going to be equal to 180 degrees, which means 90 plus 2x is going to be 180 degrees. And therefore 2x is going to be 180 minus 90, which means 2x is going to be 90 degrees or x is going to be 45 degrees. That means each of these base angles, is going to be 45 degrees. So let's mark these angles. So these angles are therefore 45 degrees. This is 45 degrees and this is also 45 degrees. Let's assume that each of these equal lengths is x, right? And now it is possible to calculate the hypotenuse using the Pythagoras theorem. So I would say using the Pythagoras theorem. AC square is equal to AB square plus BC square, which means AC square is equal to x square plus x square, which is equal to 2x square. So AC square is equal to 2x square, and therefore AC is equal to under root of 2x square, which is under root of 2 under root of x square, that is equal to root 2x. So this length is therefore equal to square root of 2 times x. Now we have all the three sides of the given triangle. Now is it possible to calculate the trigonometric ratios? Let's find out. So now I want to find the trigonometric ratios for angle 45 degree. I can pick any particular angle as my angle of reference. So I am going to pick this particular angle as my angle of reference, and let's calculate the trigonometric ratios for the given angle of reference. So the 6 trigonometric ratios, let us first find the 3 trigonometric ratios, sine, cosine, tan, and then calculating cosec, sec and cot is not difficult. You just have to take the reciprocal. So let's take sine 45. Sine is defined as opposite upon hypotenuse, right? So sine 45 will therefore be the side which is opposite to 45 is x. So it will be x divided by the hypotenuse. The hypotenuse is root 2x. And now x cancels. The value of x cancels. Therefore the value for sine 45 is given by 1 by root 2. Similarly, let's find the value for cos 45. So cos 45, we know that the abbreviation for cos was ka, which is cos is adjacent upon hypotenuse. The side which is adjacent to 45 degrees is again BC. That length is x divided by the length of the hypotenuse is square root of 2 times x. Now again in this case x and x is going to cancel, and therefore you get 1 upon root 2. So cos 45 is also 1 upon root 2. Let us now find tan 45. So tan is TOA. So tan 45 can be written as opposite upon adjacent. The side which is opposite to 45 is x, and the side which is adjacent to 45 is also x, and x upon x is equal to 1. Therefore, you notice that we can now find the values of sin 45, cos 45 and tan 45. Sin 45 is 1 by root 2, cos 45 is also 1 by root 2, and tan 45 is equal to 1. So let me pause for a minute, just take a look at what was done in this particular case and how we found the trigonometric ratios for 45 degrees. Okay, now let's take a different angle, but before that, let's start filling up the table for standard angles, for the trigonometric ratios of standard angles. So we have this table over here. Let's fill in the values that we know. We know that for 45 degrees, sine is 1 by root 2. Let's fill in the value. Cos 45 is also 1 by root 2. And tan 45 is equal to 1. You will notice that tan is also sine by cos. So 1 by root 2 divided by 1 by root 2 gives you 1. So that's another way of finding tan for any given angle. Now let's continue and find the trigonometric ratios for angles 30 degree and 60 degrees. So let's consider an equilateral triangle, triangle ABC. Let each of these sides be marked as x. So all the three sides are marked as x. Because this is an equilateral triangle, each angle is going to be 60 degrees. So let's mark each of these angles as 60 degrees. Okay. Now what we are going to do is, we are going to draw an angle bisector from the vertex A. Now this is a property of an equilateral triangle, that if you draw the angle bisector from the vertex A or from any vertex, that particular angle bisector is also going to be the altitude as well as the median. Let me quickly show you what it means. This particular angle bisector divides this 60 degrees into two parts. So this particular portion is going to be 30 degrees. So let us mark these two angles. Because the vertex angle is 60 degrees, I have drawn the angle bisector. When I draw the angle bisector, it is going to bisect the angle, meaning the angle is going to be 30 degree each, right? Both these angles are 30 degrees. Now if you take triangle A, let's mark this particular point as D. The whole measurement is BC is equal to x. Let's mark that as well. This whole measure is equal to x. Now I know that in triangle ADC, this angle is 30, this angle is 60. So therefore angle D, angle ADB is therefore going to be 90 degrees because of the angle sum property of the triangle, right? These two angles are adding up to 90 degree, 30 degree and 60 degree add up to 90. And therefore this particular angle is going to be 90. This particular angle is going to therefore be 90 degrees. Now, because angle D is 90, I can conclude that AD is the altitude. AD is the altitude. AD is also the angle bisector. AD is the angle bisector. And now, if I take triangle ABD, the left triangle and the right triangle for congruency, you will notice that by ASA test, these two triangles are congruent. There is a 60 degree and there is a 60 degree in this triangle as well. There is a 30 degree and there is a 30 degree in this triangle as well. And AB is equal to AC. So by ASA test, these two triangles are congruent. Because these two triangles are congruent, it means that BD is equal to TC by CPC-TC. Correct? So we have learned these concepts in congruency. So because BD is equal to DC, this whole length of X, the base is X. So the whole length of X can now be divided into two equal parts. So BD is therefore going to be equal to X upon 2. And DC is also going to be X upon 2. So now what we have done is, in an equilateral triangle we have drawn the angle bisector, and now suddenly we have two right angle triangles, and each of those right angle triangles contains a 30 degree as well as a 60 degree. So now let us find the length AD. So what we are going to do is we are going to ignore one half of the triangle. Let us now stick to triangle ABD. Let us ignore the triangle ADC. So now in triangle ABD, I can apply Pythagoras theorem. So by Pythagoras theorem, why am I using Pythagoras theorem? Because now I am trying to find the length of AD. So by Pythagoras theorem, X upon 2 the whole square plus AD square is equal to X square. And therefore X square by 4 plus AD square is equal to X square, which means AD square is equal to X square minus X square by 4. That is equal to 4x square minus x square divided by 4, which is equal to 3x square by 4. So AD square is therefore equal to 3x square by 4, which means the length AD is equal to square root of 3x square by 4. So square root of 3 becomes root 3, square root of x square becomes x, and square root of 4 becomes 2, right? So this particular length is therefore root 3x upon 2. Now we have all the three sides of the given triangle. This is a 30, 60, 90 triangle. Why is it called a 30, 60, 90 triangle? Because the angles of this particular triangle are 30, 60 and 90. And now we should be able to find the trigonometric ratios of 30 degrees as well as 60 degrees, because the lengths of the value of x is now, or the lengths of the three sides are known in terms of x, correct? So let's go ahead and find the trigonometric ratios for 30 degrees first. So sine 30, so now I am considering 30 as the angle of reference, right? With respect to 30 degrees, x by 2 is the opposite side. So let's mark that. We have x by 2 is the opposite side and root 3x by 2 is the adjacent side. So sine 30 is therefore equal to, the opposite is x by 2. So we know that sine is opposite upon the hypotenuse and the hypotenuse is x. Therefore this becomes x upon 2x. And x cancels, so the answer is equal to 1 by 2. Let us find the value of cos and tan. So cos 30 degrees is equal to, the adjacent side to 30 degree is root 3x by 2. So it is root 3x by 2 the whole divided by the hypotenuse, which is x. And therefore this is root 3x upon 2x. X cancels, therefore this is root 3 by 2. Similarly, let's find tan 30. Tan is opposite, that is x by 2, divided by the adjacent, which is root 3x by 2. And therefore, this becomes x by 2 into 2 by root 3x. 2 by root 3x. 2 cancels. So 2 cancels and x cancels. And therefore, the value of tan 30 is 1 by root 3. So we have found the trigonometric ratios of 30 degrees now using 1/2 of the equilateral triangle. These are the values, and now let us go ahead and let us fill these values in the trigonometric table that we had plotted earlier. So now we have the trigonometric ratios of 30 degrees. Sin 30 was equal to half, cos 30 was equal to root 3 by 2, and tan 30 was equal to 1 over root 3. So now let's go ahead and find the trigonometric ratios for 60 degrees using the same triangle. Before I find the trigonometric ratios for 60 degrees, I am going to leave you with this slide for 1 minute so that you can just take a look at all the working at how we came to this conclusion, how we use the Pythagoras theorem, and how we calculated the values of these three trigonometric ratios for 30 degrees. So let us now find the trigonometric ratios for 60 degrees. So now that we are finding the trigonometric ratios for 60 degrees, the angle of reference is now going to be this particular 60 degree angle. So let us start finding sin 60. With respect to this 60 degree now, the definition of adjacent and opposite will switch. So the opposite side to 60 degrees is going to be root 3x by 2. So this is the opposite side, and the opposite side to 30 degrees is the adjacent side, we don't need the 30 degree. The adjacent side to 60 degree is x by 2. So with respect to 60, the opposite side is root 3x by 2, and with respect to 60, the adjacent side is x by 2, and x remains the hypotenuse. So let us now find sin 60. Sin is given by opposite by hypotenuse. With respect to 60, the opposite is root 3x by 2. So this is root 3x by 2 divided by the hypotenuse. Hypotenuse is x. Therefore, because this becomes root 3x by 2x, xx cancels, therefore the answer is root 3 by 2. Let's find cos 60. Cos 60 is given by adjacent by hypotenuse. The adjacent side is x by 2 and the hypotenuse is x. So this becomes x divided by 2x again x cancels and I get 1 upon 2. So cos 60 is equal to 1 by 2. And let us find tan 60. Tan 60 is given by the opposite side, which is root 3x by 2, the whole divided by the adjacent side, which is x by 2. I know that this is division of two fractions. So when I have division of two fractions, I convert it into product of the fractions, but the second fraction is taken as its reciprocal. So x by 2 has become 2 by x, and division has been converted into multiplication. 2 cancels, x cancels. Therefore, the value of tan 60 is root 3. So we have now calculated the trigonometric ratios for 60 degrees using 1/2 of the equilateral triangle. Let me again leave you with this particular calculation for a minute, and then let's fill these values of the trigonometric ratios of 60 degrees into our table. So let us fill these values in the table now. So we found the trigonometric ratios for 60 degrees. Sin 60 is root 3 by 2. Cos 60 is 1 by 2. And tan 60 is equal to root 3. So if you notice, we now are missing the trigonometric ratios for 0 degree and 90 degree. So let us find a way to find the trigonometric ratios for 0 degree and 90 degree. So let's consider this triangle ABC and let theta be angle A. So this is the angle under consideration. So theta is the angle under consideration or angle of reference. Now with respect to theta, I know that BC is the opposite side. So BC is the opposite side. Then AB is the adjacent side. And AC forms the hypotenuse. So AC is the hypotenuse. Let us now write the three trigonometric ratios for theta now. So we have sin theta. Sin theta is going to be equal to opposite side, which is BC, divided by the hypotenuse, which is AC. Similarly, cos theta. Cos theta is going to be adjacent side. The adjacent side is AB, divided by the hypotenuse is AC. So let us have some space between these. And now we have tan theta. So tan theta is going to be opposite length, which is BC, divided by the adjacent length, which is AB, right? So these are the three trigonometric ratios for the angle theta. Now start imagining that this particular length BC starts reducing to 0. So now think about the following situation. where this particular point C that we have drawn, this point C starts moving towards B. So what I mean by that is, imagine that this point C starts moving down to B. If you notice, as C starts moving towards B, the value of theta starts becoming 0. Do you see that? I will show it again. Assume that the point C starts moving towards B. Now just keep seeing what happens to theta on the right side. The value of theta, the angle between AB and AC, starts reducing to 0. At this particular point, maybe it is maybe 2 degrees, and as you decrease it further, it becomes 1 degrees. And when you make it even lesser, it is maybe 0.1 degree, and it starts becoming closer and closer to 0. At this particular point, maybe the angle is close to 20 degrees. Then it becomes 10 degrees. This is maybe a 10 degree. This is maybe a 5 degree angle. Then this reduces to maybe 2 degrees. And now this is maybe 1 degree. And as the point C starts merging with B, you will notice that as C merges with B, you will notice that the value of the angle starts becoming closer to 0, right? And therefore, as it merges, I can say that the length of BC also gets closer to 0 because the separation between B and C reduces. So BC becomes closer to 0 and the length AB becomes closer to AC, right? So lengths of AB and AC become closer to each other and length BC becomes closer to 0. Now because BC is getting closer to 0, the numerator gets close to 0. So this becomes 0 divided by AC, which is equal to 0. As BC becomes closer to 0, this becomes 0 divided by AB, which is equal to 0. So sine 0 is therefore 0 and tan 0 is also 0. Whereas let us look at what happens to cos. Now because AB and AC become close to each other, they are almost equal. I will show this again. If you notice, I have drawn the line segment AC. Now as I pull C down towards B, you will notice that the length of AC and AB almost become equal to each other, which is why AB divided by AC will be equal to 1 because the numerator and denominator are equal to each other. Therefore, I can say that sine 0 is 0, cos 0 becomes equal to 1 and tan 0 is also equal to 0. We have found the 3 trigonometric ratios for the angle 0. Again, just to summarize this again, I started moving the point C towards B. Now most of you might be wondering that if the angle becomes 0, how does a triangle even exist for you to apply trigonometry? But what I'm trying to say is, imagine that the angle is so small that it is almost 0, and as the angle becomes closer and closer to 0, the length of BC becomes 0 and the length of AB and AC start becoming equal to each other. Now using this concept, we were able to find sine, cos and tan. So sine theta is therefore opposite length, which is BC upon AC. Cos theta is the adjacent length, which is AB upon AC. And tan theta is the opposite upon adjacent, which is BC upon AB. So as BC tends to a 0, the numerator here tends to a 0. And therefore sine 0 is 0 and tan 0 is 0. And the value of cos 0 becomes AB upon AC, which is equal to 1, right? So this is how we form the trigonometric ratios for the angle 0. I will pause for a minute. I will leave you with this particular slide and then we will go ahead and fill this in our trigonometric table. Let us now go ahead and fill this in our trigonometric table. So we saw that the value of sine 0 was 0, the value of cos 0 was 1, and the value of tan 0 is 0. Let us now go ahead and calculate the trigonometric ratios for 90 degrees. So let's consider a right angle triangle ABC where theta is the angle of reference. With respect to theta, I know that with respect to theta, I know that AB is the opposite side, BC is the adjacent side, and AC is the hypotenuse. Let us now write the trigonometric ratios for angle theta. So what is sine theta going to be? Sine theta is going to be the opposite, which is AB, divided by the hypotenuse, which is AC. Cos theta is the adjacent side is BC, divided by the hypotenuse, which is AC. And tan theta is going to be opposite, which is AB, divided by adjacent, which is BC, right? These are the three trigonometric ratios. Now, if I want to find the trigonometric ratios for angle 90 degree, what I'm going to do is, so this is the triangle that we have right now. What will happen if this point C starts getting closer to point B? So if you notice, the value of theta starts getting closer to 90 degree, right? Again, I'll show this again. Right now, maybe theta is 70 degrees. As it gets even closer, the value of theta will rise to 80 degrees. And now maybe it is going to be 85 degrees. And now maybe it is 89 degrees. And as C gets even closer to B, the value of theta will keep getting closer to 90 degrees. So here what I'm saying is, as C gets closer to B, I can say that theta gets closer to 90 degrees, and as C gets closer to B, BC length gets closer to 0, and the lengths of AB and AC get equal to each other, right? So now let's substitute this in our three trigonometric ratios. I know that sine theta is AB by AC. Now as theta gets closer to 90, AB and AC are getting closer to each other, which is why sine 90 is going to be equal to 1. Cos theta is given by BC upon AC. So BC is getting closer to 0. So this becomes 0 divided by AC, which is equal to 0. Right? So cos 90 is therefore 0. Let us write this. Sin 90 we saw that is equal to 1. Cos 90 is equal to 0. And now let's figure out what is tan 90. For tan 90 you will notice that the denominator is 0 because BC is getting close. BC gets closer to 0. And AB is some finite value. So AB upon 0 becomes infinity, or we call it undefined, right? Therefore, the value of tan 90 is undefined, also represented by infinity, because any number divided by 0 tends to infinity. So this is how we calculate the trigonometric ratios for angle 90 degree. Let me again leave you with this particular slide, and then we will fill these values in the trigonometric table. So let us fill the value in the trigonometric table. So we saw that sine 90 was equal to 1, cos 90 was equal to 0, and tan 90 was undefined or infinite. So now we have the complete table for all our standard angles. There has to be some pattern that you should notice in this particular table. Do you notice that cos and sine are actually interchanged? Just take a look at what I'm doing. You will notice that the trigonometric table or the trigonometric ratio sine and cos are exactly swapped, meaning sine 0 is cos 90, sine 30 is cos 60, sine 45 is cos 45, sine 60 is cos 30, and sine 90 is cos 0, right? So if you can remember sine, then you can definitely remember cos because it is just read in the opposite direction. So now, is there a way to remember sine and cos? Of course there is. There is a very nice technique that you can use. Imagine that you have square root of 0 by 4, square root of 1 by 4, square root of 2 by 4, square root of 3 by 4, and square root of 4 by 4. 0 by 4 is 0 and square root of 0 is 0. Square root of 1 by 4, square root of 1 is 1, square root of 4 is 2. 2 by 4 can be simplified as 1 by 2. Square root of 1 becomes 1. Square root of 2 becomes root 2. Square root of 3 by 4 is root 3 and square root of 4 is 2. And 4 by 4 is 1 and root of 1 is 1, right? So this is how you can use square root of 0 by 4, square root of 1 by 4. So 0, 1, 2, 3, 4 are basically the column numbers. So if you can correlate the columns with the angles, then it is going to be really easy to calculate these trigonometric ratios. And cos is the exact opposite of sine. Now, how can we find out tan? So, three important numbers in mathematics would be 0, 1, and infinite. Of course, all numbers are important, but these are the ones which hold some special value, or there's some special relevance to these three numbers. So 0, 1, and infinity are those three special numbers. And then in between you have 1 by root 3 and root 3, which are the reciprocal of each other. You will notice that sine always increases. So the value of sine increases from 0 till 1. Right? As you increase the angle, the value of sine increases from 0 to 1. The value of cos is decreasing always. So this is a decreasing function. Whereas tan also increases from 0 till infinite. Right? So this is the trigonometric table for all the angles. I will now leave you with this particular table for a couple of minutes, and we end our today's session over here. we conclude our session here today. I hope you understood the trigonometric ratios of these different standard angles. It is required to memorize this particular table. You should know the trigonometric ratios for these standard angles. And we will solve more questions on these trigonometric ratios for standard angles in our next sessions.